Okay, thank you very much for the introduction, and thank you to everybody who's taking time out to talk or listen about great earthquakes today for about an hour. I'm taking a break myself from analysis of a recent very big earthquake in the Bonin Islands. It's the largest deep earthquake that's ever been recorded there, and in fact, it's the deepest major earthquake that's been recorded since 1900. But as big as it is, it's a 7.9. It wouldn't even qualify to be talked about in what I'm going to lecture on today. So um, that emphasizes how big the earthquakes I'll be talking about are. Let's see, clear my screen. Okay, I'm going to talk about the earthquakes that are shown in this figure, which is a map of where great earthquakes have happened around the world going back to 1900, all the green dots. And for events in the last 10 years, you see a focal mechanism, which is a um, determination of the faulting geometry for each of the earthquakes that have happened in this 10-year period that have magnitudes greater than 8. So seismologists define great earthquakes as those with a seismic magnitude measure greater than 8, and for that we use the moment magnitude scale because that gives an accurate estimate of the very long period ground shaking from earthquakes. And what you'll immediately see is that the earthquakes that have happened in the last 10 years, the blue focal mechanisms, are in the regions where prior great earthquakes have happened for the last century. So they're not departing from what we would expect in terms of the historical occurrence of great earthquakes. What is surprising is that the number of them is quite high for a 10-year interval. There were 18 magnitude 8 or greater earthquakes in this 10-year period, which goes back to December 23rd, 2004, when the Macquarie Island earthquake struck. And that gives an apparent rate, of great earthquakes about 1.8 per year, which is about 2.5 times larger than the rate of great earthquakes for the prior century. So it's a temporal surge of activity, but you can see it's quite spatially distributed, though there are clusters of events, and part of the large number of events that has happened is because earthquakes have interacted, notably along Sumatra, where you've had 5 great earthquakes happen within just a few years. There has been a cascade of interactions there, so some of these events are causally linked. Others are so far apart that they probably are not. And yet the overall temporal concentration of events in this 10-year period has raised a lot of eyebrows as to whether there was some kind of global phenomenon occurring. I don't think that there is, but it has been tested statistically and deterministically to try and find connections between these great events. And only on the regional scale have such connections been pretty convincing. If you look at the time sequence of the large earthquakes, this is major earthquakes with magnitudes larger than 7.5 as a function of time from 1900 up to present. We start around 1900 because that's the first time that we have sufficient seismological observations around the world to measure magnitudes pretty reliably. Probably all events are shown here that are greater than 7.5. It should be fairly complete, though the early magnitudes may be a little bit more variable than recent determinations of MW for events post 1970 or so that we've got pretty reliable uniform determinations of long period moments for. The older events are more uncertain, but nonetheless you can see that in the last decade, post 2004, there's been a large number of large earthquakes over here. And this is where if you count the events above the magnitude 8 great earthquake threshold, there's 18 of them, quite a few. If you compare this burst of activity over here to what has happened before, there have been prior surges of large earthquakes or great earthquakes around the world, and notably between 1952 Kamchatka and 1965 Rat Island. This interval had significant activity, particularly above magnitude 8.5. A comparable number of magnitude 8.5 events and larger have happened in the past decade. But it includes the 1960 Chile earthquake, which sort of dwarfs all the others. It's got the largest moment, 9.5, and we have not experienced that great of an earthquake in this past decade. Another interesting thing about this tendency to cluster, and there have been some arguments that there had been an early 1900s cluster, but that's been diminished as we've revised magnitudes over time for the earlier events. perhaps most dramatic about these two clusters, though, is the period in between, which is what I call the quiet time. It really extends from 1965 up to 2004, where you did not have an earthquake larger than 8.5. So this is quite a long interval in which really great earthquakes were not happening. There was, of course, a comparable interval from 1920 to 1952. So perhaps this is the normal fluctuation that we might expect in random occurrence of events around the world. Notably, in this time, I started graduate school here in '78 and was a student at Caltech until '83. The great earthquakes really just shut down, and it was right at the time where there were first development of waveform modeling capabilities. The first moment tensor inversions were coming online, and it was the early days of expanding digital seismic recording globally that eventually prompted the systematic deployment by IRIS and by other international partners such as Geoscope of broadband seismic networks around the world. And that begins pretty much in the mid-'80s and goes, in large numbers. So there are broadband instruments going back to Grafenberg in the late '70s. But the IRIS GSN is deployed systematically over the next couple of decades, and that was commenced right when the great earthquakes were pretty quiet. So in the early days, most of these events that were around magnitude 8, some of them are great earthquakes, some are just large, they were analyzed by those progressively expanding global broadband seismic networks. In this time frame, around 1990, they began to deploy high resolution GPS instrumentation, primarily in campaign mode, so we go out and be repeatedly occupied, didn't have much time resolution. But then by early 2000s, several countries, notably Japan, the US, began to operate continuous GPS networks within their countries or in a few foreign deployments. And that over time has really expanded over the last decade. Post-2004 Sumatra, there was a big expansion of the NOAA DART, deep water ocean pressure, seawater pressure devices that are deployed. Initially, there were only 5 of them in 2004, with 1 operating at the time of the Sumatra earthquake. And they deployed quite a few more after Sumatra, and I think are up to about 65 stations around the Pacific where they have deployed these deep water pressure, ocean bottom pressure sensors. So there's been a lot of instrumentation expansion. IRIS played a huge role in this, and UNAVCO and the GPS networks, and many other groups have contributed to GPS, and NOAA in the DART expansion. So that just happened, perfect timing to capture signals from these many large events. Okay, so certainly the earthquakes themselves are occurring on a very active planet. There's plate tectonics on the Earth. And the margins of the Pacific, which is highlighted by this seismicity distribution and by these plate boundaries, are where the majority of earthquakes are concentrated, including the very biggest earthquakes. So we've understood plate tectonics, well, it's increasing well since about the mid-'60s, now well developed, and we understand that this process is responsible for the accumulation of strain on plate boundaries that is manifested in sudden earthquake sliding, that releases energy and catches up sort of in arrears with the prior large-scale plate motions. Now, if you look at the history of great earthquakes or large earthquakes around the margins of the Pacific, early on, this goes back to 1979, paper by McCanadall, they recognized that there are regions that have had big earthquakes that have happened relatively recently. So in the 1950s, there were a lot of events along the Rat Islands, Fox Islands, the Alaska event, up on the Aleutian Alaska arc that have basically released strain that had accumulated there for on the order of a century in most cases, perhaps as many as 900 years along Alaska. And that those regions, they've had a strain reduction that's accommodated a lot of the accumulated deformation from plate tectonics. And so they would identify these as regions of a recent large earthquake with relatively low seismic potential for a repeat. And this idea was codified in the seismic gap theory, which has been sort of much debated over the past few decades. And other regions that have had earthquakes historically in the past, like along Sumatra, had not had an event in 1979 since 1833 or even longer ago. And so they were colored red as sites where they know that great earthquakes have happened in the past, but they haven't happened for a significant fraction of the estimated recurrence interval, or at least a significant time if we don't know the recurrence interval. And that includes places like the southern San Andreas, where the 1857 earthquake on the southern San Andreas, probably about 7.9 magnitude, is the site where we would expect that there's potential for a future earthquake, a near future earthquake. And those areas they colored red. Now, if you look at the red stars, this is where 11 of the recent 18 great earthquakes happened. And it's, you know, much as this seismic gap idea has been criticized as not having really high statistical value, the reality is it actually predicted or anticipates the locations of most of the recent very great earthquakes. So at some level, they have occurred where there was large strain accumulation, and that is not terribly surprising. These were areas that we had flagged as having that potential, notably along the 2010 rupture zone in Chile, the 2014 Iquique earthquake. These are happening in well-recognized seismic gaps that had been instrumented. But of course, it's not simple, and even along Japan, there was uncertainty in the size of the largest credible earthquake, and we had not had a direct recording of a magnitude 9 earthquake, and generally that surprised people that such a big event would happen there. But this is a testimony to what we have kind of understood about where big earthquakes are likely to happen, and pretty much how well they have conformed to the expectations. And you know, I'm not going to debate the statistical estimates in these, but I think there's a lot of merit to the basic idea of the seismic gap approach. Nonetheless, there have been great surprises with most of these events, and that's been why the availability of extensive broadband seismic networks and GPS networks and tsunami networks that have increased in size over the decade of these events. It's been so important to have all that data. It's revealed surprising attributes that might have gone undetected were these events as poorly recorded as earlier events in the century from 1900 up until about 1970 or so. And I'm not going to go through all these details, but this just highlights almost every event has had some interesting story. Solomon Islands, to pick one that I will talk about. It ruptures right across a triple junction. We'd never observed that and sort of thought it wouldn't happen in qualitative ideas of the occurrence of big earthquakes. The Sumatra earthquake ruptured 1,300-kilometer long fault, the longest rupture that we've observed. We've seen the entire megathrust rupture in the 2011 Tohoku earthquake off Japan with slip up to 60 meters, the largest amount of slip. There have been just a sequence of surprising attributes that we've been able to quantify with the available seismic data. So what I'm going to do in this talk is highlight just a subset of these events, a few of the interesting aspects, and more or less how we're studying them, how we're exploiting these seismic, geodetic, and tsunami data sets to come up with a kind of better characterization of the complexity that great earthquakes can experience, and hopefully we can translate that into better information about what to expect in future large events and how to mitigate their effects. Well, let me begin with Sumatra because that's where the story began in 2004 with the 9.2 earthquake on December 26. It ruptured this entire length, the long region of the plate boundary, about 1,500 kilometers long, where there had been prior events in the northern area, 1941, 1847. These have been magnitude 7.8 or 8 size earthquakes. And we might have expected there to be a large earthquake down along Banda Aceh. There had not been a historical record of one, but plate tectonic convergence rate could have accumulated significant strain there. But nobody anticipated that this event would reach as far to the north as actually rupturing past the Nicobar and Andaman Island arcs and through these regions that had ruptured previously. And over here, the plate motion between the Indian plate and this upper plate, which is sort of a Burma sliver, is almost arc parallel motion. So they would not have expected there would be that much strain accumulation for convergence, and yet all along that rupture zone it thrust. Soon after, just a couple of months after the 2004 event, the March 2005 magnitude 8.6 earthquake happened right next door. And this is pretty readily identified as an aftershock expanding away from the nucleation point of the 2004 event. And then a couple of years later, in 2007, you have a large earthquake down in central Sumatra, which is ruptured right here. It's an 8.5, had a magnitude 7.9 aftershock. So these three giant events are on the plate boundary. They're interplate thrusting. And in 2012, you have a sequence of strike-slip faults rupture in the offshore. One of them is in a single cascading sequence rupturing 4 or 5 major faults. It says a magnitude 8.7, and it had an 8.2 aftershock on this fault. So Sumatra's been hit hard with 5 of the great earthquakes in this decade. It's also experienced large earthquakes at shallow depth. These are major earthquakes, 7.8 earthquakes, very near the trench, along Java and along the Mentawai region here. This area here, which last ruptured in 1797, is the Mentawai Gap. It's a lot of concentrated monitoring this region because it's between the rupture zones of the 2005 earthquake and the 2007 event. So right in here, the Mentawai Gap is deemed to be a high probability area for a future earthquake. Now in 2004, we didn't have all these stations, but we were well on the way to having got most of these stations. This is a 2008 map of the global seismic network. Most of these were operational and available in 2004 and have been upgraded to have this type of instrumentation, which is a STS-1 instrument, which is exposed here with the lid off. And that broadband instrumentation, which had been deployed since the 1980s or so, recorded on-scale motions for the 2004 earthquake globally. And this profile, it's kind of a famous profile, I think Rick Astor originally put this together, of ground motions as a function of distance from the source origin down at 0 to the opposite point on the Earth, which is near the Galapagos, 180 degrees away. You're seeing the biggest amplitudes here, the Rayleigh wave R1 arrivals and R2 arrivals and R3 arrivals. Having all of these motions on scale, with the exception of very close in, where even the STS-1 instruments will go off scale, provided an unprecedented data set for a magnitude 9.2 earthquake. We did not have anything comparable to this for earlier events in the century. We had made, by painstaking efforts, digitized R3, R4, R5 earthquake recordings for the 1960 and 1964 great earthquakes, but this type of digital data was unprecedented at the time. It's largely the efforts of IRIS to collect this data just in time for the 2004 event that was so important. Now we can take those waveforms and model them and completely exploit the seismic recording information from around the world to understand the source, to map how the slip spread over the fault as a function of space and time. These are just examples of waveform fits for the complete long period ground motions. At the time, though, in 2004 in December, we didn't have regular routine capabilities for doing this that were operational. In fact, the earthquake, because it was so much larger and had such a much longer rupture duration than any of the events that we had experienced during the 1980s and 90s when we were in that quiet time, we had developed algorithms that could work very well for magnitude 7 earthquakes, maybe even up to magnitude 8. But this magnitude 9.2 earthquake, rupturing 1,300 kilometers, it lasted for over 450 seconds. And that meant that we had P waves and S waves coming in on top of each other in the later part of the rupture after 3 minutes. And nobody's algorithms really could disentangle that. We were not prepared to analyze such complicated, long duration rupture. And it took a couple of months for the community to improve collectively the algorithms. And when I was chair of the board for IRIS, we worked on putting this together to get community consensus models developed by March or so of 2005. So within 3 months, we were able to produce a model like this. This is a slip distribution. So the color contours tell you how much slip. In almost all cases, the slip is pretty much perpendicular to the trench along here. And you can see the rupture zone for 2004 extending farther north, and then this is the rupture of the March 2005 event. And it's spotty. There's intermittent 10 to 20 meter slip patches along this. And we can determine this type of slip distribution from the type of waveform modeling I just showed, where we can fit the entire waveforms, or you could fit just P waves or S waves and try to analyze their complete interference patterns over this very long rupture. But it took a couple of months to get that type of slip distribution. Now, GPS technology had also been deployed prior to 2004, largely in campaign mode around Southeast Asia. There had been many campaign observations. They caught the motions before and after. So this is just a GPS sensor. It's looking up at a constellation of GPS satellites. At the time, we were just using GPS. Now we'd be using a greater network of GNSS instrumentation for the future. But this GPS sensor then measures very precisely the position, and as you do it at different times, intermittently deploying the instrument, you can get the changes in position before and after faulting and make maps like this. This is developed some years after the Sumatra earthquake, I think is when this is first published, can measure the amount of motion of the stations relative to a fixed reference frame here taken somewhere down in the Indian plate. You can see these large oceanward slip measurements that are several meters or many meters of displacement. And then as you get further away, there's smaller amounts of displacement. There's a great GPS data set for this event as well. Now, because it's campaign mode, and at the time we weren't having much telemetry, was not available for analysis for about a year. I think I saw the first real GPS analysis. So for the Sumatra earthquake, we had very rapid determination. Aftershocks, we had some methods like the CMT, and this was a multiple CMT that Victor Tsai applied when he was at Harvard with multiple sub-events. This is after 3 months, the slip distribution that was obtained from seismic wave inversion. And then these other models, which all are dated 1 or 2 years after the earthquake, are various seismic or geodetic inversions, and they're characterized in the slip. Now, there's a lot of variation between the models, but in general, they are consistent in showing patchy, intermittent slip, which is peaking around 20 meters. It sort of differs in some of the models as to whether it extends all the way to the trench or not. But in 2004, this was transformative. We suddenly had the first detailed characterization of slip variation pretty reliably resolved relative to any of the earthquakes of the last century, where we may have had just a handful of records. And for the 1960 Chile earthquake, for example, there's only less than a half dozen on-scale recordings of the early part of the rupture from the P wave through the S waves. So there's a tremendous change in the quality and quantity of data available by 2004. The next large earthquakes that occurred were in 2006, 2007, the next great earthquakes. And this was an interesting pair. It was an event which happened where the Pacific plate is underthrusting the Kuril Island arc, so Sea of Akats over here. And it was a typical underthrusting type of earthquake. But what was interesting was that it occurred in a region of the trench where there had been uncertainty in the seismic coupling. Historically, there had been only a few events located in this region. We didn't really know their mechanism. And it had been thought that because the region along this stretch of the arc is different, it has a big four-arc basin, it's got disruption of the volcanic chain here. People had speculated that maybe the coupling was different here and it could not support a great earthquake. But in November of 2006, it in fact had this magnitude 8.4 thrusting event that ruptured all the way to the trench. And it was a very substantial earthquake, pretty straightforward rupture with a more or less bilateral slip distribution and slip up to 10 or 15 meters. It was tsunami-genic, but all these islands that had former Soviet military installations had been abandoned. There was a naval base here, a submarine base, and they had pulled all that out, so there was not much local damage. And there's only a handful of campaign GPS measurements that have been made along here. So it was mainly analyzed by seismic waves to determine the slip distribution. And this shows the pattern of slip, and these little vectors are the direction of motion of the upper plate relative to the lower plate. And what was most distinctive about this November 2006 event was that it immediately activated little earthquakes in the outer rise. That's very commonly observed for large interplate thrusting that as a result of the strain change on the megathrust, the outer rise may experience a transient extensional stress increase, and that activates normal faulting. But in this case, it activated really big normal faulting. So while there were little events immediately within a few tens of seconds of the occurrence of the thrusting. Out here it just bubbled along for a couple of months, but then on January 13th, 60 days after the November 2006 rupture, there was another great earthquake, and it was this event with a normal fault. So we have a great thrust and a great normal fault, 60 days apart, separated by about 50 kilometers. And this made this an extraordinary doublet of events, because this is a triggered aftershock, but it's a distinctively large event. It's an 8.1 versus an 8.4, and it has a different focal magnitude. And it ruptured along this region with very large amounts of slip. This event's a higher stress drop, actually produced stronger shaking in Japan than did the interplate thrusting event. There had been prior, in 1963, outer rise compression, then this normal faulting, then a couple of years later, this outer rise compression again. These compressional events are deeper in the plate than the normal faulting. That's shown in this cross section, which is a vertical cross section. This is the megathrust plane, which ruptured in 2006 in November. So you have about 5 meters of slip on that. 60 days later, as a result of the strain change in the Pacific plate here, you activate this normal faulting. So you can think of it kind of pulled on the plate and activated, snapped a rupture that extends perhaps 30 kilometers down into the plate with this magnitude 8.1 event. And then a couple of years later, you have deeper compressional faulting. So this is a commonly observed phenomenon in the outer rise, where shallower extensional faulting, deeper compressional faulting, consistent with bending, but it's this stress state is clearly being modulated and activated by the interplate convergence cycle, which produced this magnitude 8.4 earthquake. In 2007, on April 1st, there was another great earthquake that was particularly interesting. It happened in the Solomon Islands. This is the area that I had done my very first paper in seismology. I'm working on large earthquakes up in the northwestern section of the Solomon Islands. And that area was distinctive in that there are very large earthquakes, and great earthquakes, they always tend to happen in pairs, or they commonly happen in pairs. So there's a lot of doublets there. They tend to be thrusting type earthquakes that have doublets. And in the study I had worked on with Hiro Kanamori back in 1980, we had looked at the Solomon Islands to the southeast, and this area had not had any recorded earthquakes. There were big pairs of earthquakes up to about this point. To the southeast in this area, right along this region, there was no recorded great earthquakes, and we thought that might make sense, because in that area you have a transition of what is being under thrust. Here the Solomon Sea plate, a fairly young plate, is under thrusting the Pacific plate along this subduction zone. The Australian plate is under thrust down here. And in between the Solomon Sea plate and the Australian plate, it's sort of there's ridges, and there's this actual spreading region which has formed the Woodlark Basin. So this is a plate boundary coming in and intersecting this other plate boundary. So this is a triple junction right here. It's a junction between the Solomon Sea plate, which is subducting relative to the Pacific in that direction, the Australian plate, which is going this direction, and these two vectors are not parallel as a consequence of the motion that occurs on this plate boundary. So this area, we're subducting very young oceanic material formed very recently at ridge, and it's actually, there's other rift segments here. So you're subducting very hot, presumably relatively weak ocean crust. And we thought, well, you just won't have a big earthquake there, because it's hot, it's crossing the plate boundary, it's buoyant, it's weak, et cetera, et cetera. And of course, all that was falsified by the 2007 event, which began on the Australian plate subduction side, ruptured a patch here, but then it spread right across, triggering another patch over here. And there were two large patches, this on the Australia-Pacific boundary, this on the Solomon Sea Pacific boundary, failing in one magnitude 8.1 earthquake, right across the triple junction, right where we think there is actually not even slab going down. There's a slabless window that opens up from this triple junction point due to the divergence of the Australian and Solomon Sea plate. And here you had a rupture at shallow depth go right across this region. This is very tsunami-genic. The rupture extends up to the trench, and that's even more forcefully reinforced by analysis of the tsunami signals. We were just analyzing the seismic signals at the time. The next couple of, our next great earthquake that occurred happened along the Peru subduction zone. It was the Pisco earthquake in 2007, magnitude 8 earthquake. It's pretty much a run-of-the-mill earthquake in the sense of magnitude 8. It was a typical 100-kilometer long rupture, and happened in a region where we expected there to be large earthquakes just north of where the Nazca Ridge is subducting, which is an area that putatively might have a weaker boundary and might be an obstacle for ruptures to go. And it ruptured in that region. But we were interested in it and began to analyze the signals from it, finding that it actually had an unusual story. This is the slip distribution obtained for that earthquake. And what we found is that the rupture began with a fairly concentrated rupture near the hypocenter, which was about a magnitude 7.8 earthquake. And then the rupture went into a hiatus. It just stopped, or it spread very slowly without much energy release. And 60 seconds later, it picked up, and there was an even larger magnitude 8 rupture that took over and spread on the other side of this little peninsula and caused a large tsunami to come in. So this was sort of a compound earthquake. It was a doublet, but very close together, 1 minute apart, where clearly the larger follow-up faulting had been triggered by the earlier faulting. Now, this presents a lot of problems for efforts like earthquake early warning, because you could analyze this first event, think it's all over, because after 60 seconds nothing is happening, and then immediately get a bigger earthquake that's coming in that you might not be prepared for in your early warning system, because you kind of shut it down after the first minute so that you don't get a false secondary trigger on S waves or something. So this is a real problem. Well, being interested in Peru, then we look back at the 2001 earthquake. This is a little bit before our decade surge, but this event was an 8.4, a larger earthquake, ruptured along this region. It's in the rupture zone of the 1868 southeastern Peru earthquake. So this was a re-rupture of a long-standing seismic gap, at least the northern half or 2/3 of that gap. And in detail, when we looked at the signals from that earthquake, we also found that that event had initiated with a smaller magnitude 7.5 earthquake, very concentrated. And then there was a hiatus and slip as the waves propagated out. And by the time the surface waves reached this position about 100 kilometers away, initiated strong new rupture, which expanded actually back toward the initial rupture at shallower depth. So we had an event occur that was of modest size, 7.5. It dynamically triggers a larger follow-up earthquake that was ultimately to grow into 8.4. And if we analyze the signals kind of as a single inversion, you kind of get an oscillation or a reversing of the slip distribution going southeast and coming back northwest. Instead, I think it actually was a discrete precursory event that triggered this 8.4 that spread bilaterally and appears to come back to the northwest. Both of these present real problems for earthquake early warning approaches that we need to keep in mind. 2009 had another very curious event. This is the Samoa earthquake that ruptured at the northeastern end of the Tonga Arc. This is where the Pacific plate is coming in from the right. It's going off in this direction. This is the northern end of Tonga, and it goes down to the south to New Zealand with the long stretch of fault along Tonga and Kermadec. And right up in this region, the Pacific plate is ripping. It's tearing because it goes right through over to the Marianas in the north, and here it must subduct. So it has this complicated intraplate deformation. In this region in 2009 in September, there was a large normal faulting earthquake, and then it had this mechanism. This was the fault plane that we found for the earthquake and the slip distribution, a large amount of slip in it, 20, 30 meters of slip. And it was in the Pacific plate, so it's within the subducting plate in this strongly contorted region where you're going around a bend and tearing of the Pacific plate. But when we analyzed the signal and we got a slip distribution fairly quickly, we recognized that there were some problems. In particular, an unusual aspect was that if we analyzed with W phase the radiation at very long periods, we got an incompatible mechanism relative to what the GCMT, which was measuring somewhat shorter but still long period information. This level of inconsistency is very unusual and suggested that there was additional rupture process going on, and that it wasn't just a normal fault rupturing here. Another clue was when we look at the aftershock distribution, the red dots indicate the aftershocks are all over the place, not many of them being on this fault, but there's many that are along what appears to be either the upper plate or along the plate boundary of the northern end of the Tonga subduction zone. Prompted by work that Chenji had done and presented at AHU, we further analyzed the detailed waveforms of this earthquake and found that, in fact, it wasn't just a normal fault, that it had triggered dynamically thrust faulting. These are two sub-events of the overall thrust faulting that occurred at positions 2 and 3. This is on the boundary between the Pacific Plate and the northern Tonga block of the upper plate here. And they represent a mix then of normal faulting and thrust faulting that together give us this difference in long period interference patterns that are manifested differently depending on what frequencies you analyze the signals at. So again, triggered earthquake, doublet process, normal faulting triggering thrust faulting in this case, which is illustrated in this cross section that had a normal faulting event occur within the subducting plate, activating thrust faulting. It's just the reverse in time from what had been observed in the Kuril events, where we'd had the 2006 thrusting activating normal faulting. This was recognized by a single GPS station by John Bevan. He saw that that station had moved eastward. The normal faulting should have moved westward, and he said, well, there has to be a thrust faulting. He didn't know when it happened because it was campaign data. He didn't have any time resolution. The seismic waves tell us that it happened after the normal faulting. Now, there may have been some slow slip before, but the sequence is resolved by seismic waves in this case. That brings us to the great Tohoku earthquake with along Japan, the Pacific Plate's under thrusting Japan. The classic story is that the plate boundary is locked and you have deformation before the earthquake. Now, in this case, there's a lot of GPS before the earthquake, and they can see this stage. So Japan had put a lot of GPS stations on the island, and they could see that when the boundary is locked, it will drag the coastline in the direction of the subducting plate. And when it ruptures, then that will reverse. And you'd see patterns of uplift and subsidence before and after the earthquake, or co-seismic with the earthquake. So we had a lot of GPS stations deployed after the Kobe earthquake in 1995. Japan invested greatly in its infrastructure, and these are all high-rate GPS. They were quickly processed and made available within a few days. So it's a tremendous difference from just 7 years before in 2004. These data were quickly made openly available. And you can see that these little vectors all heading toward the west. This is before the earthquake, for the deformation was occurring in about a 10-year interval before 2004. And that is the time when the boundary out here is locked and it's dragging the eastern side of Honshu and Hokkaido toward the west. I said east. And you can see there's a gradient so that the western side of the islands are being deformed less than the eastern side. They're close to the fault, the locked fault. And from that, you can map out regions where there is strain accumulation and potential for future earthquakes. And at the time this map was produced before the earthquake, there was recognition there could be large earthquakes off of central Honshu and also off of Hokkaido. But the maps show almost all the strain accumulation being very deep on the megathrust from 30 kilometers down to about 45 kilometers. The up-dip region, they just couldn't tell. They didn't know if there was a locking there or not, but this was an indication that we could expect there to be future earthquakes. And there have been earthquakes of up to magnitude 8 along that coast over the last century, so that was consistent with the expected hazards. What happened was a much bigger event than expected occurred, caused co-seismically large springing eastward of the eastern side of Honshu, and you can see as you go to the west, you'd spring forward less. So it really was the accordion motion of building up strain and releasing it that is responsible for these co-seismic displacements. Now, the earthquake produced a great global seismic data set. We analyzed the seismic waves to determine this slip model. This is showing the magnitude of slip and the direction of slip of the upper plate relative to the lower plate. And what's interesting is the very darkest red contours, the biggest slip vectors, are on the order of 60 meters, which was really quite dramatic. And instead of being concentrated down in the region where the geodesy had suggested there was most of the coupling, the slip goes all the way across the fault, 200 kilometers wide, rupture zone, and the slip is maximum up in the upper 50 or 60 kilometers, at least in this seismic model. There's some question about this. This was produced in the first couple of days after the earthquake, and we were surprised that this could be an instability. It does, however, if you predict what the GPS motions are for this model, it does a good job of matching the basic length and directions of the GPS. This is purely a prediction, not an inversion at that time. So we were surprised that there was such large slip out at the trench. Now the GPS data themselves, because they're high rate, could be analyzed not just for the total seismic offsets, but you can measure the time varying components of the GPS. And so these are not seismic orders, but these are GPS ground positions as a function of time for stations along the Honshu coastline. And what you see in the east direction is that the motions over about the first 100 seconds, there's a little wiggle, and then it goes to some static permanent deformation. This is the 52 or 0.52 meter eastward surge of the coastline up to a couple of meters in this case. All of this energy, which is varying with time, is constituted of P wave and S wave and near field terms and Rayleigh and Love wave, all the seismic wave arrivals that are building up within them the overall time varying deformation and the contribution to the near field terms that give the static offset. Well, this is observations in red and synthetics in blue, which can fit very well. So you can take these data and invert them just as you would a seismic wave field, except now you have to use Green's functions that contain the full deformation, the permanent static deformation, and you can invert that for slip distribution. Here was a seismic only model. Here's a model inferred just from inverting the high rate GPS. And there's general similarity, a large 200 kilometer wide fault, peak slips of 60 meters at the trench. Some differences to the south, and this is not well resolved in the seismic model. Other models producing very similar results from seismic waves. I believe all of these are seismic inversions, looking like this initial model. So the seismic models give a fairly consistent story. There's some differences with the GPS, but in general, they're compatible on the order of 50 to 80 meters of slip in the upper plate. Now, separate analysis of these seismic waves and GPS waves has sort of been the standard because the distinct seismic and geodetic communities that analyze these earthquakes. But when we study large earthquakes, we're interested in getting time resolution, spatial resolution, resolution of the moment as a function of position and time. That's not uniquely resolved by any one type of data set. So body waves, teleseismic body waves give good time resolution. Surface waves give better moment resolution without good time resolution. GPS, if you just have campaign GPS, you have no time resolution at all, but you can get good spatial resolution if the stations are well located. The same is true with INSAR and other methods that measure the ground deformation, but they're limited to the deformation on land. Tsunamis have good spatial resolution offshore, but not very good time resolution because of a very long period, though they provide useful information on space. Now, if we can use all these different types of waves together, we can get the best overall solution for the slip distribution. So an example for the Tohoku earthquake, here we put in high rate GPS stations, seismic surface wave observations, seismic body wave observations, and invert them together. If you invert them separately, you get different models. This is slip distribution from high rate GPS, from just seismic. So this looks like the models we were showing before. This is from the surface waves. It's sort of a little bit more spatial resolution than the body waves in this case. And when you put them together and do a joint inversion, you get sort of a mix of these models that, if you're careful in the merging of the data set and the inversion, you're able to exploit the complementary sensitivity of the different data. And that's put into map view here. This is a joint inversion of these different types of data. And this is kind of the standard of what people are doing now. Whenever the data are available, we try to put GPS and seismic data together when it is possible. Now, this event also produced giant tsunami, and the tsunami was recorded by the Japanese. They had again put off many sensors offshore that are these little white dots. These are ocean bottom pressure sensors, and they record the incoming waves as they're approaching the coastline. These are basically buoyed systems or cabled systems where they have ocean bottom pressure sensors, These are getting time from communication to satellites, and they may be transmitting data, or they may be linked by cable to provide that data. Or in the case of these early offshore stations, some of the offshore stations, they also have GPS capabilities from the ocean bottom. Now these, and this is the current distribution of dart buoys around the Pacific that greatly augmented after the 2004 Sumatra earthquake. Now for a given earthquake rupture model, this is a seismic model. It's rupturing at 1 minute to 2.5 minutes time. This shows the area that has slipped and how much it has slipped cumulatively at each interval of time. This represents the corresponding deformation, the seafloor bottom, predicted by the slip at depth, the dislocation occurring on the fault. And this is then a calculation with a nonlinear wave code NeoWave that accounts for the dispersion during the uplift of the ocean bottom relative to the sea surface. And this is the sea surface deformation. And then once this deformation happens very rapidly, within 2.5 minutes, gravity acts on it and causes the wave to spread. The spreading wave goes much slower than the initial rupture, and at 10 minutes, this is the crust of waves coming in toward the coast. Around 20 minutes, it begins to hit some of these ocean buoys, and by about 30 minutes, it's impacting the coast. It sweeps up on the coast. Now, between 15 and 25 minutes then, these offshore buoys record the seafloor pressure with traces, the black traces, the actual recordings, and the red traces are predictions of what should have been seen based on the seismic model. So in this case, the seismic model does very good at predicting the timing, amplitude, and shape of the tsunami, and that's because it's coupled to very accurate bathymetric calculation of the tsunami for the time-varying uplift of the seafloor and the corresponding deformation of the surface of the sea that spreads out in the gravity wave. And you can also go offshore or out to the ocean to these dart recordings and model very simple pulses, but you can get very detailed, longer period oscillations within the near coastal environment. So we can predict the tsunami very well in that case. And that raises the possibility of doing the joint tsunami and seismic conversion. I haven't done that, but others have worked on that for the Tohoku earthquake, but I'll show a couple of examples where we've done it. One will be for the Mentawai earthquake. This is the magnitude 7.8 earthquake that ruptured very near the trench. It happened just up dip of the 2007 great earthquake. So this is not a great earthquake, but it produced a much bigger tsunami on these islands than this much bigger magnitude 8.4 earthquake. That's because it ruptures to shallow depth, and the large slip at shallow depth generates strong tsunami that sweeps in on the islands. This was a model first obtained just from seismic waves only, and it's just got limited spatial resolution. So we could add in additional tsunami observations, Cocos Island, a dart buoy, the Padang, there's a tide gauge measurement there, and there's a deep water buoy right at the northern end of the rupture deployed by the Germans. And in addition, there was a lot of GPS data along the Pagai Islands and the Mentawai Islands in the north, and also on shore. These are part of the sugar array deployed by initially Caltech and now operated by Singapore. If we take those different data sets, we have high rate GPS, teleseismic data, and tsunami data. We want to know how to combine them and what they can resolve. One way to test that is to use a standard checkerboard test where we put in a finite expanding rupture, but it has a complicated slip distribution of large slip, no slip, large slip, no slip in this type of checkerboard. It's a time-dependent calculation. You construct the GPS solution on all the sites that you have. You construct the tsunami solution. You predict the teleseismic waves and invert them separately to see how well you can recover this known input slip. The GPS recovers quite well the pattern close to the islands and down depth. It does fairly well offshore, actually, in this case. The teleseismic waves have very limited spatial resolution in this case. The tsunami does quite well offshore, but it doesn't do so well down depth. And when you put them all together, this kind of, by balancing the relative sensitivity information, you can do a better job of recovering your input model. You can get good fits to the tsunami observations here at the top. These are GPS observations. These are seismic, just examples of the data. So the joint inversion works, and when you do it to the real data, you get this type of slip distribution which is now much more concentrated near the trench, up to 20 meters of slip or so, 15 to 20 meters of slip, much more concentrated than our seismic only inversion. That's a result of being able to fit the GPS and the tsunami, this is the closest tsunami observation, very well. So the joint inversion strategy is very valuable for that tsunami earthquake. The last example would be the Chile earthquake of 2010. It's also one that we've worked on with all the different types of data sets. About a 500-kilometer long rupture along the coast of Chile, under thrust in the Nazca Plate below Chile. Now, this region had very good GPS instrumentation. Many of these are campaigns, some of them are continuous. And before the earthquake, they were all moving to the eastward, indicating the plate boundary over here, where there were big thrusts in the past, was locked. You can map the amount of slip deficit or strain accumulation that's occurring along there and identify regions that have large strain accumulation close to 100% slip deficit relative to plate motion. That means it's really locked and building up strain right in this area where the earthquake is going to occur. But it's kind of patchy, and this does depend a little bit on how you treat the upper plate deformation in the Andes and whatnot. So it's not a unique mapping of the deformation. But you can see that's the expected behavior before the earthquake, and then when an earthquake happens, it's going to spring to the west. What we have for this earthquake are good high-rate GPS observations from in the vicinity of the rupture. The rupture is in this box here. Offshore tsunami observations to the north. These are NOAA DART. The Chileans have subsequently deployed darts along the coast of Chile, which will greatly improve the resolution. And then there are INSAR looks from a couple of different directions, INSAR passing by, looking at line of sight deformation of the ground. So giving kind of a continuous supplement to these high-rate GPS, though these are intermittent. These are kind of like having campaign measurements at each one of these points sometime after the event. In addition, there's a lot of teleseismic, seismic, or P waves, S waves, and surface waves. We'll invert the body waves here. First, a quick reality check with a similar checkerboard. This is an input finite source model. We specify a rupture expansion, calculate each type of data set from the actual observation positions, and invert them to see how well we can recover. The high rate GPS, which has limited number of stations right here, it does fairly well local in to where the stations are, but it does poorly out on the edges. The teleseismic inversion is not terrible in this case. It does better on the eastern side of the fault. The INSAR does great for the continuous deformation of the land. It recovers the structure very well, but it does very poorly offshore. The tsunami, complementarily, does very well offshore and does terrible onshore. There's really no excitation here. So by judiciously weighting and combining the data set, you can get a joint inversion that now begins to more or less accurately recover the actual input slip model. Real data, you do the same thing. These are fits, data and fits to the GPS, the seismic tsunami observations, and this is the residual fit of the INSAR data. So the data are quite well fit in the joint inversion. In this case, well, these are the final slip models, the slip of 20 meters in this patch, and there's another patch down here. The region right in the center, very low slip, but has a large number of bigger aftershocks. These are CMT aftershocks, GCMT, and they're to the north. They kind of bracket the areas of large slip, which is commonly observed. Here there's a bit more overlap. And there's extensional faulting in the outer rise. So there was induced outer rise extension, as we'd seen off of the Kurils, but it didn't make such giant events. So this earthquake was another great example of how well you can do when you have the different data sets and invert them together. So what have we learned from this recent spate of earthquakes? Well, the first thing is that most of our ideas of where and when great earthquakes will happen they've been somewhat limited. We were right that they're going to be near plate boundaries. That's in fact the case. Many of them were in areas that have been recognized to be seismic gaps, so we're having some progress in understanding them. We've seen different scenarios of behavior, though, some of which were surprising. We've seen migration of activity like 2004 Sumatra, 2005 Sumatra, 2007. We've seen that type of migration before along the Aleutian, Alaska margin, so that type of migration has been observed. We've not observed rupture across triple junctions or subducting ridges as dramatically as in the Solomon Islands, so now we really have to be rethinking some of our ideas of how disruption of the subducting plate may affect coupling and the ability of rupture to spread across. The Mentawai earthquake is one of a handful, maybe there are 9 shallow tsunami earthquakes that rupture updip of either large prior events like the 2007 event in the case of Mentawai 2010, or this region may just be creeping and you have events like we've seen along Java, rupturing right up to the trench, producing very large tsunami because of shallow slip right close to the ocean bottom. The Tohoku earthquake ruptured the entire width of the fault zone, re-rupturing areas that had been thought to be characteristic size earthquakes, magnitude 7.8 to 8 down dip, instead rupturing with very large slip all the way to the trench, so kind of compounding the tsunami excitation by the occurrence of very strong tsunami earthquake-like component to the rupture. That is the best example that we've seen of that type of whole plate boundary rupture. We've seen thrusting trigger normal faulting, as in the Kuril Island sequence. We've seen normal faulting trigger thrust faulting, as in the Samoa sequence. So we know that strong interactions and complexity can occur. I haven't been able to talk about the 2012 strike slip events offshore of Sumatra, which rupture on 4 or 5 planes. That's also a great demonstration of rupture complexity. We're still at the point of trying to understand, well, what controls the heterogeneity. The most of the effort has gone on the megathrust, which there were 11 great megathrust earthquakes in this last decade, and the others are intraplate. The megathrust appears to be heterogeneous. We still have a asperity idea that seems to be relevant, which is the idea that there are zones of discrete frictional properties and strain accumulation, so that these red patches will be areas where you have large strain accumulation, high frictional strength that seems to build up and release intermittently. May rupture as a single big event or a cascade of events going along the plate boundary separated by some period of time. Sometimes these ruptures can drive into the shallow region and rupture the entire width of the fault, or you may rupture down dip and then separately activate shallow tsunami earthquake failure at very shallow depth. This has very strong tsunami excitation, but typically slow rupture, distinct properties of radiation relative to these deeper, large patches that control the big earthquake. As you go deeper on the megathrust, it appears that the characteristic asperity scale reduces and you have higher frequency contributions, more small patches rupturing during large earthquakes that generate strong high-frequency shaking. You can find a lot more details in this review paper. So let me wrap up. I appreciate your indulgence in this kind of quick discussion of great earthquakes. We're now really in a much better position than even 20 years ago in terms of having the data and instrumentation in place to monitor pre-seismic and post-seismic deformation before great earthquakes. They do happen sort of where we expect them to happen in a general sense on the plate boundaries. So the concentration of instrumentation in those regions is valuable. But there are many areas where we still have very sparse GPS instrumentation and limited tsunami observations. So there's many places that we could instrument better in the future that would help us when earthquakes strike there. Systematic deployments of these instrumentation has paid off a great bounty in terms of allowing us to comprehensively model all the ground motions and the tsunami excitation and propagation. And that's giving us much better information about these earthquakes than we've seen before. So thank you for listening to this, and I'd be willing to answer any questions that you might have. I know I've gone through a lot of details quickly. You can find all my publications for download at this website. All the papers are available there, so you're welcome to download and look at those. And if you have any follow-up questions after doing that, I'm happy to chat with you as well. Thank you very much.
Great. Thank you very much, Thorne. That was a fantastic overview. So we have a few questions already queued up. I would encourage folks, as I read through these initial ones, to submit questions as well. So let's kick it off. Here's a question from Robert Watts, and he asks, is there any relationship between the location of great earthquakes and the subduction rate where they occur?
Well, there's a significant variation in the subduction rates amongst the regions that have had great earthquakes recently. So it's not a simple relationship, and there's not a simple relationship with the size of the earthquake and the subducted lithosphere age either. So We know, for example, along Cascadia that there have been magnitude 9 size earthquakes repeatedly. That's subducting relatively young ocean at fairly slow rates compared to what might be going on along the Japan or Sumatra regions.
All right. Next question is from James Garrity, and James asks, I tend to think of great earthquakes as dominantly on the megathrust. In this decade, 11 of 18 are megathrust, the rest intraplate. Did previous episodes of bursts of great earthquakes have a similar proportion that were intraplate rather than megathrust?
Well, that's a really good question, and it's part of the frustration of our limited record for the older events, where even the magnitudes have pretty big uncertainty, much less the focal mechanisms. We do know that in the 1950s to 60s surge of big earthquakes, we know the mechanisms of the very biggest ones. They were all studied pretty much by Hiro Kanemori and a few others, and they were interplate thrusting events for the most part. So there have been large normal faulting events before this recent surge, so we'd seen events like that, but the Samoa earthquake, the Kuril normal faulting earthquakes are among the very biggest normal faulting events that we'd observed in oceanic plate that we knew the mechanism for. So there have been efforts to go back and analyze what available WSSN data or older data people can access and try and constrain the mechanisms. The majority of the very big events, as best we can tell, are probably thrust events in the past, but I have no question in my own mind that there have been some mixing of other mechanisms into that data set, and that events were, like for the Samoa, there's a compound faulting with normal and thrust faulting. We simply wouldn't recognize it for earlier events.
All right. Question is from Juan Lee, and Juan is curious about the earthquake that you mentioned right in your introduction. He's asking, can you tell me a little bit more about the most recent deep earthquake that occurred around Bonin, Japan, with the depth of 690 kilometers?
Well, yeah, I'm actually taking a break from writing a paper on it now because we're pretty close on to our final assessment. It is the deepest major earthquake in recorded history. It's deeper than the biggest events in Fiji or in Java. It's very isolated. It's a good 100 kilometers from the nearest prior seismicity. And it has, at least in the USGS catalog, only one 4.9 aftershocks. So it's very devoid of aftershocks. The rupture took about 17 seconds. It's got a somewhat oblique normal faulting mechanism looking at the surface, but it looks like it's associated with distortion and deformation of the subducting Bonin plate, where in the north along Izu it goes horizontal. In the central part where this event occurred, it appears to extend vertically. So there's some deformation along strike of the plate. And it's a very high stress drop. We're getting something on the order of 85 MPa.
Great, thank you. Question from Alessandro Vuan, and this goes back to that figure that you showed very early on about the great earthquakes over the last 100 years. He's asking, he says some authors have found this 55-year time interval for fluctuations in these, and I think you pointed that out. And he's asking, do you think a single physical phenomena is able to modulate that sort of fluctuation?
Well, I guess I would argue that any assignment of an interval is probably premature. There's just not that much confidence in the magnitudes of the turn of the century events in the early 1900s, and so I think it's just accentuated by a few events in the 50s and 60s that you would get this type of apparent interval. I don't think you can extrapolate backward. Some efforts have been made to do so because there are historic records and catalogs that do go back longer in time for the very greatest earthquakes, but they're likely biased. When people try to estimate whether there's any significant periodicity in there, they're working with a very limited database. So my own sense is it's almost pointless to speculate about it. Well, it's very straightforward to take the distribution of earthquake magnitudes and the number of them from the actual record and just randomize them and draw them out and get distributions that look similar to what we have. So that's why we cannot falsify the idea that these are Poissonian and totally random, apparent surges or apparent intervals of enhanced activity. That's a very common outcome of simply randomly drawing from the same population of magnitudes. So at this point, statistically puzzling over it, it's sort of interesting, but I don't think it's well constrained, so I don't have much more to say on it.
Okay, thanks. Well, I don't have any other questions queued up right now. Maybe I'll give people another second just to type those in if they're interested. But I just wanted to, make the note that we had a full house today. If I know I got a couple notes that people, we ran out of space, so this will be posted. Probably try to get it up this afternoon. And I just wanted to say thanks again, Thorne. I thought this was a fantastic talk. I hope that you're able to have some good experiences giving this across the country.
Yes, thank you very much. I appreciate everybody listening in, and any comments, welcome to email me at tlay@ucsc.edu. And otherwise, I'll be giving a slower pace and a little bit more of an entertaining version of this at 4 different museum venues over the next few months, and trying to fly the flag of IRIS NSF in doing so. So thank you very much.
Yeah, much appreciated by us. So thank you again, Thorne. Thanks everybody out there who attended. And as Thorne said, if you have any follow-up questions, you're welcome to email him. So thanks again, everybody. See you next time.